we're going to be studying electromagnetic induction today. This is the experiment first carried out by Michael Faraday in England and independently by Joseph Henry in the US in 1831. They both found that moving a magnet near a conductor produces electricity. Of course, it's a relative motion that's important. Moving the coil over a fixed magnet also produces electricity. Producing an EMF using a magnet is called electromagnetic induction. EMF is an old term meaning electromotive force. Let's look at this in detail. If I move a single wire through the magnetic field of this magnet, the galvanometer will measure an induced current. If I move it so that it cuts across the field lines, I get a maximum EMF and a maximum induced current. If I move it so that it goes parallel to the field lines, however, I get no EMF and no current. If I use several turns of wire, I get several EMFs in series and the effect is much larger. That's why it's easiest to use this, to demonstrate this effect, using a solenoid, which is a whole lot of coils in series. Now there are so many turns that the induced EMF is much larger. Notice that the speed is important. I move the magnet slowly and I get a smaller EMF but for a longer time. If I move the magnet quickly, then the EMF is larger, but it doesn't last as long. When the magnet stops, the induced EMF stops. It's actually the rate of change of magnetic flux that causes the current in the conductor. Pulling the magnet out of each of these coils in turn will give an induced current proportional to the number of turns. Remember that we've got 3 coils, one with 250 turns, 500 turns, and 1000 turns. Now let's try different areas of coils. Using a large area, we get a significant change. We get a significant induced EMF. But if we reduce the area, then the EMF is much smaller. So we can see that the induced EMF is proportional to 3 things: the number of turns in the coil, the rate of change that it cuts the magnetic field lines, and the area of the coil. Faraday discovered these relationships and summarised them in what is now known as Faraday's law. The induced EMF is proportional to the number of turns, the area of the coil, and the rate of change of magnetic field. In this device we've got a coil of wire that will rotate and cut the magnetic field of this magnet. As it rotates, it will cut through the magnetic field lines and change the magnetic flux. So we can use this weight to convert the mechanical energy of this falling weight into electrical energy. However, you can see that there's going to be a problem here because when this side cuts past the north pole of the magnet, the current will go one direction, and when it comes around here and cuts past the south pole, the current will go the other direction. This will give us alternating current. This device takes up too much room. Normally a generator is much more compact and the coils are in a smaller area, much like in this device here, where you can see that it has more coils over a smaller area and within the magnet. And of course, the faster it's turned, the more induced EMF you get. We can also look more closely at how the coil actually connects to the circuit now. We can see that one end of the coil is always connected directly to this ring, which is connected always to this part in the circuit. As it passes this pole of the magnet, the current will go one direction, but when it cuts the magnetic field of the other pole, then the current will change because it's still connected to the same point in the circuit. This is called alternating current, or AC. We can connect this up to the galvanometer and see that the current actually changes direction as we turn the coil around. To stop the current changing direction, we can actually split the ring and connect only one side of the ring to one side of the coil. So that this side of the coil, when it passes this contact, will be going in one direction, and then when you turn it round, it connects to the other side of the coil that is still cutting this pole. So the current will always keep going in the same direction. So on this device we can switch from AC to DC. This generating device can also act as a motor if we connect a power source to it. Well, now we can change the generator into a motor by putting current through the wire, which creates a magnetic field around the wire. That magnetic field, when it passes the poles of this magnet, will oppose it and force it to travel in the one direction. When it gets around to here, the current's been reversed. We're on a different pole of the magnet, so the force is going to be the same direction. Remember from before we found that a magnet moving in a coil induces an EMF in the coil. Instead of just using the magnet, we can make an electromagnet out of this coil. By connecting this coil to power, it creates an electromagnet. We can now move that magnet around this secondary coil, which changes the magnetic flux around this secondary coil, which in turn induces an EMF. What we can also do is leave the coils together and turn the power on and off. By turning the power on and off, I'm turning on and off the electromagnet, which changes the magnetic flux, which induces an EMF in the secondary coil. We can strengthen this effect by using an iron bar to strengthen the magnetic field of the primary coil. Now the induced EMF is even larger. What we can also do is place them both directly on a single core. The iron core is now a complete circle, so virtually all of the magnetic flux of the primary passes through the secondary coil. So the induced EMF is very large indeed. So which direction does the induced EMF flow? Well, we can think about it. If we have our magnet moving through a conductor, then that induces an EMF in the conductor, which induces a magnetic field. Now, if that magnetic field would add to this magnetic field, then that would induce a bigger EMF, which would induce a bigger magnetic field and a bigger EMF and a bigger magnetic field and an even larger EMF until it just blew up. So obviously that just couldn't happen in our universe. So what it does is it opposes the direction. Like in this experiment, if I bring in the north side of this magnet like this, then the current will flow in this like that to oppose the direction. So that the north side of this magnetic field will be this way, which means that they will repel each other. If I try to move away and decrease it, then the loop will again oppose this change. So whatever the change in magnetic flux, the induced EMF will always oppose it. If, however, I bring in the south side of the magnet, then the current will be flowing this direction, which will induce a current flowing this direction in the conductor. And again, they will still repel each other. The direction of the induced current is such that its magnetic field always opposes the change in magnetic flux. Thus, the conductor actually has to carry current. If we have, as in this case, an incomplete loop, even though we make an EMF, there's going to be no current running through because of this gap. So there's going to be no magnetic field opposing this magnet. Next, we're going to look at the electromagnetic induction coil. Okay, let's look at this device and its circuit. We've got an EMF power source that connects to a coil, that then connects to this saw blade, and then this contact when the saw blade joins it, which connects back to the EMF power source. This saw blade is actually springing in and acts like a switch for this circuit. When it's closed, then the circuit is complete and current will flow. When it's open, then current won't flow. When it is closed, then current will flow, and it will flow through this coil, which because of the iron core will act like a strong electromagnet. That magnet will attract the saw blade, and that will open the circuit, and so current won't flow, which also means in turn that this electromagnet won't be an electromagnet anymore, and the switch will close. So when we have the power on, it should oscillate between these two places. There are two reasons why we might want to do this. One would be to have this movement, in which case we'd try and reduce our voltage so that we didn't have the spark. The other would be if we wanted to have a high voltage spark. This is further evidence of Faraday's law. Because we're changing the current so quickly, turning it on and off, we're getting a large magnetic flux change through the electromagnet, which in turn causes a large EMF, or a spark. This is another version of the same device, which actually goes a little bit faster than the other one. So I can bring in the secondary coil and make a much bigger spark between these 2 points. Whenever conductors move in and out of magnetic fields, eddy currents are set up. These act to oppose the change. With the pendulum swinging normally it's okay, but when I connect the electromagnets, then they'll cause small eddy currents in the pendulum, and those currents will have magnetic fields that oppose the change and the movement of the pendulum. Eddy currents within the actual aluminium are actually real circuits, much like this. When I move this circuit through the magnetic field, it induces a current. The magnetic field of that current will oppose the magnetic field of the electromagnets, which will cause the pendulum to stop. Let's look at the effect of temperature on induced current. this is a sort of transformer. The primary coil is an electromagnet and the secondary coil is an aluminium ring. When the primary coil has the power turned on, the magnetic flux will increase through the secondary ring. Let's suppose that the current flows this way through the primary coil so that the north pole is facing upwards. Then the induced EMF in the secondary will oppose that change and the current will flow this way and it'll be a coil with the north pole pointing downwards. So that when I turn the power on in the primary coil, the secondary and the primary will oppose each other. Let's now cool the secondary ring in liquid nitrogen so that there will be less resistance and more current will flow. Therefore, there will be a larger repulsion. That went higher.